Hi everyone. In today's video, we will discuss the Lorentz Force Law, the key to how electric motors, generators, and speakers work. From your headphones to high-speed trains, this law powers motion from electricity. Let's explore how magnetic fields and currents create force and how engineers analyze it. The Lorentz Force Law is one of the most important principles that connects electricity, magnetism, and motion. It explains how electric and magnetic fields act on moving charges, and it's named after the Dutch physicist Hendrik Lorentz, who unified these ideas into one elegant equation. In its general form, it is expressed as shown in the equation below, where F is the force acting on a charged particle, Q is the charge, E is the electric field, V is the velocity of the moving charge, and B is the magnetic field. This equation tells us how both electric and magnetic fields can push or pull a moving charge. But in electrical machines, we are not dealing with single charge particles flying through space. We are dealing with conductors carrying current, which means billions of electrons moving together inside a wire or coil. Now, when a magnet is placed near a current carrying conductor, the conductor itself experiences a force. This is called the Lorentz force. The Lorentz force equation used in this case is F is equal to IL cross B. Keep in mind that this equation is derived from the general equation of Lorentz force law. It tells us about the force experienced by the current carrying conductor when it is placed in a magnetic field. Here in the equation, I is the current, which is a scalar. It tells us how much charge flows but not its direction. B is the magnetic field, which is a vector. It has both magnitude and direction. L represents the length of the conductor, but here is something interesting. Normally length is a scalar, but in this equation, L is treated as a vector, and the question arises is that why it is considered as vector. The answer is because we also need to know the direction of current flow in the conductor. So the vector L points along the direction of current, with its magnitude equal to the length of the conductor inside the magnetic field. To easily find this direction of force on a current carrying conductor in the magnetic field, we use the Fleming left-hand rule. Here is how it works. Stretch your thumb, forefinger, and middle finger so that they are all at right angles to each other. The forefinger points in the direction of the magnetic field. The middle finger points in the direction of current I, and your thumb then shows the direction of force acting on the conductor. This simple hand trick helps us visualize what the cross product means, that the force, current, and magnetic field are all mutually perpendicular. In order to demonstrate the Lorentz force law, we can perform a very simple experiment. For this experiment, we will need the following components. First is a DC power supply, which will provide electric current for our circuit. Second are the current carrying rails, a green platform with two binding posts, one red and one black terminal. The red terminal is connected to the positive side of the power supply, and the black terminal is connected to the negative side of the DC power supply through the red and black wires respectively. Third is the current carrying conductor, a brass rod that we will place across the top of the two conducting rails, allowing current to flow through it. Fourth is a permanent magnet's horseshoe magnet with a red side and a blue side. The red side represents the north pole of the magnet and the blue side represents the south pole. The magnetic field flows from the north pole to the south pole. Now let's understand how this setup works. Current flows from the power supply through the red terminal along the brass conductor rod and back through the black terminal, completing the circuit. When we place the magnet below the current carrying conductor, as shown in the picture, we can apply Fleming left-hand rule. According to this rule, the first finger points in the direction of magnetic field from north to south. The second finger points in the direction of current flow from red to black terminal. And the thumb points in the direction of the force on the conductor. In our setup, the current flows horizontally along the brass rod. The magnetic field points upward from the north pole to the south pole, and therefore the force should act horizontally, pushing the conductor rod towards us. Now let's turn on the power supply and observe whether the conductor rod moves in the direction predicted by the Lorentz force law and Fleming left-hand rule. As we can see, the current carrying brass rod experiences a force, and the direction of that force follows exactly what Fleming left-hand rule predicts. This confirms the Lorentz force law through direct observation. Now you might be wondering that in case of permanent magnetic electrical machines, if the Lorentz force acts on the current carrying conductor in the stator coils which are stationary, then how does the rotor actually spin? Here is the key. Force always comes in pairs. If the magnetic field exerts a force on the stator conductor, the conductor exerts an equal and opposite force back on the permanent magnets on the rotor. The stator is held fixed, but the rotor is free to move, so it spins. However, this explanation can feel indirect and not very intuitive for understanding motor operation. There is actually a much better way to visualize and understand how motors generate torque, and that's through Ampere's law. Ampere's law, which will show us how current carrying conductors create magnetic fields and how these fields interact with the permanent magnets to produce rotation. In the upcoming videos, we will explore Ampere's law in detail, and you will see a much clearer and more intuitive picture of torque generation in electrical machines. Let's look at where the Lorentz force shows up. In industry, it powers massive motors, conveyor belts, robotic arms, and cranes. In transport, it drives electrical vehicles, train motors, maglev systems, and starter motors. In your daily tech, it's behind loudspeakers, phone vibrations, hard drives, and electric toothbrushes. In healthcare, MRI machines, surgical tools, and motorized prosthetics all rely on it. In aerospace and defense, it powers satellite controls, aircraft actuators, and even experimental railguns. Bottom line, anywhere you need precise, reliable motion for electricity, the Lorentz force is doing the work. So let's wrap this up. Today we explore the Lorentz force law, the fundamental principle that connects electricity, magnetism, and motion. We saw how it acts on current carrying conductors, creating the force that drives motors, generators, and countless devices around us. We performed an experiment demonstrating the Lorentz force in action and applied Fleming left-hand rule to predict force direction, a simple yet powerful tool that visualized the cross-product relationship between current, magnetic field, and force. We also discussed how this force powers everything from industrial motors and electric vehicles to medical equipment and aerospace systems. Wherever precise motion from electricity is needed, the Lorentz force is at work. But remember, while the Lorentz force explains what happens to the conductors, understanding the motor torque through Ampere's law gives us a more intuitive picture of how rotation is actually generated. That's what we will explore later in this course. Thank you for watching. If you found this helpful, hit like and subscribe. It really helps the channel grow. The full course is available on eMotorLabs.com, link in the description. Every purchase goes straight into better experiments and better content for you. More videos on motor control, machines and embedded systems are coming. See you in the next one.